Welcome to the fifth week of live interactive session for the course Engineering Mechanics. So this week we will be seeing the topic kinematics of rigid bodies. So we'll go to the first question. A particle starting from rest at position x equal to 0 moves along a straight line with velocity v is equal to 2 t raised to 5 by 2 minus t raised to 1 by 2 meter per second. Find the time taken by the body to return to the origin. Express your answer in seconds rounded to 2 decimal places. So it's the pure kinematics. You just need to solve the differential equation. So try to solve yourself. I will give you some time, then I will explain how to do it. So in case if you found the answer, you can just put it in the chat box. We will discuss that. So remember, the velocity expression is non-linear in time, so you have to use the differential equation, basically the kinematic equation, then solve it. So did anyone got the answer? Okay, so let me explain how to do it. So we had to use the kinematic equation dx by dt equal to v, where v is given as 2t raised to 5 by 2 minus t raised to 1 by 2 in meter per second. Now if you just rearrange it, dx equal to 2t raised to 5 by 2 minus t raised to 1 by 2 times dt. Now we integrate on both sides. So x we integrate from the initial location, which is 0 given, to the final location, let's say some capital X. On the right hand side, 2t raised to 5 by 2 minus t raised to 1 by 2 dt. Again we have to integrate from time equal to 0 to some final time t. Now on the left hand side it will be x minus 0. On the right hand side it is 2 t raised to so 5 by 2 plus 1, which is 7 by 2 whole divided by 7 by 2 minus t raised to 1 by 2 plus 1, which is 3 by 2 by 3 by 2, and the limit is from 0 to t. So again applying the limits, you will get x equal to 4 by 7 t raised to 7 by 2 minus 2 by 3 t raised to 3 by 2. So this is the location of the particle at any instant capital T. This you can simplify a little bit, taking t raised to 3 by 2 common outside. So it will be 4 by 7 t square minus 2 by 3. Now question what is asking the question is that find the time taken for the body to return back to the origin. So we know at t equal to 0, if you substitute back here, you will again get x equal to 0. That's already given in the question. At initial time, it was starting from the origin. Now what other time? Again it will come back to the origin. That means for x equal to 0, is there in another time as a solution to this equation? That's what we have to find. So we will see that so t raised to 3 by 2 times 4 by 7 t square minus 2 by 3 equal to 0. That's what we want. If you solve, we'll get t square equal to 2 by 3 times 7 by 4, which is 7 by 6, or t is equal to square root of 7 by 6. So if you evaluate that, this value will be around 1.08, I think, second. So this is second after which the particle returned back to the origin. Is this clear? Any doubt? Good. So we'll move to the next problem. So here a ball is launched using a cannon of length L with an initial speed of u0 at an angle theta, as depicted in the figure. So a ball of height h with a negligible thickness is present at a distance d from the cannon. If the ball is launched so that it crosses over the wall without hitting it, then so yeah, question is incomplete. Basically you have to find what is the critical value of u0. So what should be the minimum value of u0 so that it will the ball will just pass the wall without hitting it? So that's the question. So you can try this out. It's basically a projectile motion. Just need to consider certain facts, that the projectile is not exactly starting from the ground, it's starting from the tip of the cannon, and it's starting with an initial velocity u0 with an initial angle of theta with the ground. So hint is that so you have to find the position of the ball at any instant in time for a general time, both in x direction and in y direction. Then combine both, eliminate time, and represent the trajectory of the ball as a function of x and y, where x and y are the position of the ball at any time. So then you just need to substitute when the particle reaches horizontally at the wall location, its vertical height should be greater than or equal to the wall height, otherwise it will hit the wall. So from that equation you can get a condition for the initial velocity, the critical value of initial velocity. So try this out. I will give you some time to try this. Did you got any answer? So I will explain how to do this. So basically remember that the projectile is not starting from the ground, rather it's starting from the tip, as I mentioned. So let our origin be here and measure x in the horizontal direction and y in this vertical direction. So let this point on the ground, the bottom of the cannon, be O prime and tip of the cannon be O, which is our actual origin. So so now our objective is that, see here also the initial direction in which the ball is ejected out will make an angle theta with the horizontal. See, what is the issue with assuming the ball is starting from the bottom of the cannon is that it has to travel the distance L along the cannon. It will be a straight line. It won't be part of a parabola. As you all know, the trajectory of a projectile should be parabola. Inside the cannon, its motion is actually guided through the cannon tube. So it won't be a parabola, it's a straight line. Once it is ejected out, then only it will follow the parabolic path. There only we can apply the equations, the kinematic equations for the projectile. Inside we cannot do. Inside we will just assume that it is traveling with a constant velocity u0 over the distance L. So I think that is clear. Now our assumption is that it is ejected in such a velocity that while it reaches at the location of the wall, it will just pass through its top, or it will be higher. I mean, we need the minimum velocity so that it will just pass through the top of the wall without hitting it. So if that is a situation, it's a horizontal distance the projectile traveled. That is basically if you measure, that is this distance, right, which is not exactly d, rather it's a d, total d minus the length projected in the cosine direction, right, the horizontal direction. So this length is actually d minus L cos theta. So that is it's a horizontal distance it traveled when it reached the wall. Similarly, vertical direction, it has traveled a distance which is not exactly h, rather it's h minus the projection of L in the vertical direction, right? It's L sin theta. Is that is clear? Any doubt here? So yeah, If that is clear, then everything is easy. So now we have a projectile which is starting with the velocity u0 at an angle theta. Now it is traveling. So when it reaches the wall at some particular location, it is traveling a horizontal distance of d minus l cos theta, and corresponding vertical distance is h minus l sin theta. Now we can write the equation for the projectile. Generally, let's say at any location, at a particular time it reaches, it has traveled a distance of x in the horizontal direction and y in the vertical direction measured from the origin. So how will we generally write the expression? So why do we want to write that expression is that first we generally write for a corresponding x value what will be the corresponding y value. So it will be a parabolic equation. I hope it's already discussed in the lectures. I am just going through it again. So as you know, the horizontal direction, there is no acceleration. Basically we neglect the air friction. So the horizontal component of velocity, that is u0 cos theta, which will not experience any acceleration or retardation. As a result, it's a constant velocity motion in the horizontal direction. So the horizontal distance traveled is the horizontal velocity times the time. So that's all. Now in the vertical direction, so it is experiencing a constant acceleration in the downward direction due to gravity. So as you know, is equal to ut plus half at square. This is the expression for motion, the displacement covered by a particle which is starting with an initial velocity u and experiencing an acceleration a after time t. So now in the vertical direction, the vertical distance will be, if you do the same thing here, it's u0 sin theta, which is the vertical velocity, the component of velocity in the vertical direction, initial velocity times t, plus half acceleration, which is acting vertically downward with the magnitude of g, so the sign should be negative, time t square. So I think there is no doubt in this part. Now if we just eliminate the time from equation 1 and 2, so how we can do that? From equation 1 you can write time as x by u0 cos theta. So please stop me if you have any doubt. I assume that it's already clear to you, so that's why I'm going fast. Now if we substitute this back in equation 2 for every place where time is there, so y is equal to u0 sin theta into t, right? The t is x by u0 cos theta minus half g times square, that is x by u0 cos theta the whole square. So now if you rearrange it, it's just need to cancel some of the terms. So this u0 will be cancelled. So the remaining terms will become x into sin theta by cos theta, which is tan theta, minus g x square by 2 u0 square cos square theta. So this is the expression for the y displacement of the projectile in terms of the x displacement. So basically this is the equation for the trajectory. If you see y as a function of x, you can see the functional form. Theta is a constant, which is the initial angle. u0 is a constant, g is a constant. So you can think this is like ax square plus bx. So y is equal to ax square plus bx is equation of a parabola. So that's why the projectile trajectory will be parabola. Now we will come to our problem. So we know when x is uh, the horizontal distance traveled, which is d minus L cos theta, the distance to the wall. So if x is d minus L cos theta, what we want is that the corresponding y value should be at least the wall height from the origin, which is h minus L sin theta. So if we do this, we will get the critical value. Ideally, we want the y should be greater than or equal to h minus L sin theta. If y is lesser than that, then what will happen is this will hit the wall. So we want the corresponding y value to be at least h minus L sin theta or greater than that. So substitute that in the equation 3. If we substitute this in 3, so which is the critical thing, h minus L sin theta should be equal to d minus L cos theta times tan theta minus g x is actually d minus L cos theta the whole square by 2u0 square cos square theta. So what we need to identify is the initial u0. So what is the critical value? That's what we want to find. So we just rearrange the equation. Before that, do a simplification. So in the left side it is h minus L sin theta. On the right side, if we expand, it is d tan theta minus L cos theta times tan theta. So cos theta times tan theta is actually sin theta. So it's L sin theta here minus g d minus L cos theta the whole square by 2u0 square cos square theta. Now if you see on the left hand side, we have a minus L sin theta. On the right hand side also we have the same type. We'll just cut them and do a rearranging. We'll get g into d minus L cos theta the whole square by 2u0 square cos square theta, which we bring to the left side, and we'll bring the h to the right hand side. So it's a d tan theta minus h. So from here we can say u0 square is equal to g into d minus L cos theta the whole square by 2 cos square theta times d tan theta minus h. So now if you take a square root, you can find the critical value of u0, which is d minus L cos theta by cos theta times square root of g by 2 into d tan theta minus h. So yeah, that is a solution. Is this clear?
Sir,
Yes.
sir, in the starting, we took x equal to u naught cos theta t, sir.
Yes.
I couldn't understand that, sir.
So the second point, did you understand that y equal to u0 sin theta?
That the s equal to ut plus half it.
Yeah, same only. In the equation 1, you can think it's the same way. S equal to ut plus half at square. Just that a is 0. There is no acceleration in the horizontal direction. So that you will get ut only. Is that clear?
Clear, sir.
Yeah. So basically, we are neglecting the air friction. So that's the only thing that can change the horizontal velocity. Air friction, In the vertical direction there is always gravity acting, so that we cannot neglect. For a ball we can neglect the air friction, idealized situation. So that's bad to do, but that's how we do it. Later you will learn, probably in different subject, how to account the air friction. Any other question? Okay, so I guess that is clear. So then we'll move to the next problem. So a car is traveling around a circular track of radius 50 meter. If the magnitude of its total acceleration is 10 meter per second square at the instant when speed is 20 meter per second, so then what is the rate at which the car is changing its speed? So you can see the options are given. So the unit is meter per second square. So it's asking for acceleration. Okay, so it's actually simple, so you can try this out and I'll explain how to do it. So Ashutosh have texted it is 10 meter per second square. So we will see. So so the car is traveling around a circular track, so with the velocity of 20 meter per second. Its total acceleration is 10 meter per second square. So there is two things involved. When it is going through a circular track, it will actually have a rate of change of its own speed. Also, because it is trying to move in a circular track, it will experience a force, centrifugal force or centrifugal acceleration. So the net acceleration is given as 10 meter per second square. So you have to just find the part of the acceleration which is only due to its change in velocity. So you know the centrifugal acceleration is not because of it's a change in velocity, right? It's a change in direction. So the net acceleration magnitude is given as 10 meter per second square. So the net acceleration has two parts, which is a centripetal acceleration and a tangential acceleration. Now the centripetal acceleration has a magnitude, which is just velocity square by the radius of curvature. So here if we evaluate that, velocity is given 20, so 20 square by radius of curvature is 50. So it's 400 by 50, so which is 80, right? It's 80. Eight, sorry. So this is 8 meter per second square. And now the tangential acceleration, which is the one we need to evaluate. So then from here you can write the magnitude of acceleration. So because the centripetal and tangential acceleration will be normal to each other. So let's say this is a curved track. At this location, it will have a tangential acceleration tangent to the trajectory and normal acceleration towards the radius of center of the curved path. So they will be normal to each other. So just the Pythagoras equation or the resultant value with 90 degree. So it's AC square plus AT square. So you can just evaluate the magnitude of tangential acceleration from this expression as A square minus AC square. So it's 10 square minus 8 square. So it's 6 meter per second square. So this is how the car is trying to change its velocity at this rate. Okay. Now because it's moving through a curved path, it will experience centrifugal effect also. So that is the extra 8 meter per second square. So the total effect is felt as 10 meter per second square. So that's why there can be a confusion, but I think that is clear. Okay. So we will move to the next problem. So a body is rotating about point O as depicted in the figure. At a particular time, the body's angular velocity and acceleration are 1 radian per second and 0.5 radian per second square respectively. At this instant, which of the following is true for point A on the body shown in the figure? So there can be multiple correct answers. So if you see the options, you can see you are asked to evaluate velocity of point A and acceleration of point A. So you just need to evaluate both of the quantity and check which of the option is correct. So try it out, then we will discuss it. Okay, so there is a, yeah, one comment saying B is correct. We will see. So it's an MSQ, so there can be one more correct answer. So so did you find the acceleration? So first of all, we'll look at the velocity. So the object A, the body is actually rotating about the point O. So the point O is not moving. All other points are rotating about point O. So our point A is also do the same. So it's we have to connect the point A to O. It's already connected in the figure, which is like the radius of rotation. So the velocity at the point A will be perpendicular to the that line, the connection. So it should be along this line, and according to the direction which is given in the figure, both omega and alpha are acting, and then that's the angular velocity and acceleration, both are acting in the counterclockwise direction. As a result, intuitively you can think the velocity of A will be arrow will be in this direction. So this will be the velocity vector. Now, I mean, why I'm saying this is that before finding a numerical answer, just roll out from the option which of them are can be correct and which of them cannot be correct, just by the direction. So this is VA, velocity of A. Now we need it the component form, the x component and y component. You can clearly see this is in the second quadrant if you think a quadrant about point A. So which will have an x component which is negative and an y component which is positive. So the I component will be negative and j component will be positive. So in case of velocity, you can think both A and B both have the options given as negative x direction and positive y direction. So we cannot just rule out them because both are satisfying the criteria. Now we need to evaluate the magnitude, then only we can identify which of them or which one of them is the correct one. So velocity of A, the magnitude, which can be written as so the angular velocity of A with respect to O times r to A measured from O. Right. So we have the angular velocity which is given 1 radian per second times the radius which is 2 meter. So we'll get 2 meter per second as the velocity, the magnitude of the velocity. So this is VA, the magnitude. Now which will have so now we know the magnitude, and that magnitude is acting along this particular direction. And if you see what is the direction, so if you try to resolve this into the horizontal and vertical components, you can clearly see this angle is 60 degree because here is a 60 degree. So from the basic geometry you can see that is 60 degree. So the velocity of A will be its magnitude times cos 60 in the negative I direction, it's left direction, and again velocity of A times sin 60 in the plus j direction. So now if you evaluate, its velocity of A is 2 times cos 60 is 1 by 2 minus I cap plus 2 times sin 60 is root 3 by 2 times plus j cap. So the answer will be minus I cap plus root 3 j cap. So option B is correct. Okay. Now about the acceleration. So now acceleration of point A basically will have two of the components, which is so this all because A is rotating about point O, where point O is fixed. It's a fixed point about which A is rotating. Otherwise we will see later problems how we should write the general acceleration. So now acceleration of A will, because it's rotating, it can have two components, normal component and a tangential component. So the normal component will be acting that's basically the centrifugal force. So it will have a centrifugal component and a tangential component, as we see earlier. Now we have to find the resultant of both. So first we will evaluate what is their magnitude, and then we will see what is their direction. Accordingly we will add up both and finally get to the final result, the net acceleration of point A. So first of all, the centrifugal component, so the magnitude of the centrifugal component which is just v square by r, velocity of A square by the radius of the curvature, radius of the motion, curved motion. So velocity of A we already evaluated, it is 2 meter per second. So it's 2 square over, the radius is also 2 meter, so it is 2 meter per second square. So that is the acceleration of A in the centrifugal, due to the centrifugal direction. So, so if you see point A here and this point O, the centrifugal acceleration should act along towards the center of rotation, and the tangential acceleration should act along tangentially in this direction. And as alpha is given to be a counterclockwise acceleration, so that's why we have the angular acceleration is also being along the direction of the velocity v. Okay, so now we have to evaluate the magnitude of the tangential acceleration, which is just r times alpha. We have r equal to 2 and alpha is given as 0.5, so we can evaluate it to be 1 meter per second square. Now we only evaluated their magnitude, we need to evaluate the direction so that the vector form of the acceleration can be found. So if you see here, geometrically, basically you have to resolve this forces, the accelerations into components. So this angle is 60 degree. We have seen that. Is 60 degree? Yeah, nobody has pointed out earlier, so I made a mistake. So this is not 60 degree, okay. That is so this angle will be 60 degree and this angle should be 30 degree. So if that's the case, here it will be cos 30 and this will be sin 30, and cos 30 and sin 30 will change the result. I hope you're understanding what I am saying. So the angle was not exactly 60 degree earlier, so it is cos 30 component in the x direction and sin 30 component in the y direction. So because of that, it's cos 30 is root 3 by 2 and sin 30 is 1 by 2. So the result is minus root 3i and plus 1j. So the answer should be option A for the velocity. Now for acceleration, if you come here, again this is 30 degree and that is 60 degree. You can write acceleration, the centrifugal acceleration is whatever its magnitude times cos 60 in the horizontal direction, but it's in the negative I direction. That is projection of this along the horizontal direction. Similarly, the projection along the vertical direction, which is acting downward. So it's a sin 60 in the minus j direction. Similarly, acceleration of along the tangential direction is its magnitude times cos 30 in the negative I direction, but sin 30 in the plus j direction. I don't know, is that clear to you? So basically we are saying we know the direction, in which the accelerations are acting. So if you see in the figure, the centrifugal acceleration is acting towards the center O. So we know the direction. We also know the magnitude. We are just resolving it into components in the horizontal and vertical direction so that we can associate with the I cap and j cap, where I cap and j cap are measured as a usual sense. The plus x axis is plus I cap, plus y axis is the plus j cap. So now if you see here in this figure, the centrifugal acceleration is in the third quadrant, so it should have a both x and y components are negative, so that's why you have negative I and negative j here associated with its directions. Similarly, the tangential acceleration is in the second quadrant pointing towards, so it will have the x component being negative and y component being positive. Now if you just evaluate it, so I'm running out of space here, so I'm not evaluating it, but you can try this. All the values are known here, already evaluated them, so you just need to evaluate numerically, and the final result, acceleration of A, will be just the sum of the both. So if you do that, I'll just write the final result. You should get minus of 1 plus root 3 over 2 I minus of root 3 minus half j. So which will be actually the last option, option E, in the numerical value sense. So is this clear? Okay, good. So we will move to the next problem. So in the given figure, a pin in the rotating arm OA engages the slotted link and causes it to rotate. The pin is located at a distance B from the point O. So along the rotating arm, the angular velocity of the rotating arm is 0.2 radian per second. S is the distance between the base of the rotating arm and the slotted link. If S is given 0.1 meter and B is 0.25 meter, find the angular velocity omega CB of the slotted link in radian per second when the angle theta is 45 degree. So try this out. So it's a kinematic mechanism. So we are now starting analyzing mechanisms. Yeah, so just remember the link OA is rotating about the point O. The link CB is also rotating about, so it's also rotating but about point C. Just that one of the point in the link OA, which let's call it with some name, let's say call it D, this point has both, when it has a rotating motion about the point O, it has a sliding motion as well as a rotation, rotary motion about point C, because it's part of that point is actually part of both the link AO and BC. So just remember that and try to connect between one link to another, and we can try this and then I'll explain. Okay, so I'll explain how to do this. So we can try different methods. So I will only follow one of the method. The other method we will see in the next problems. So in this particular case, beginning point will be same. So we have to find the velocity of the point D first. So now D is as consider D is the point in the link OA. So velocity of D, just magnitude only. We just need to evaluate first. So according to point D in the link OA, it's just rotating, right? Because it's a rigid rod, OA is just rotating. So it's just the distance OD times the angular velocity of the link of the member OA. So now OD is a distance which is given as B, and B is also given, which is 0.25 meter, times the angular velocity, which is 0.2 radian per second. So it is 0.25 times 0.2. So it's 0.05 meter per second. So the velocity of D, now we know. Now we need its direction. So as we have seen in the earlier problems, it should be perpendicular to the member, right, along this way. So this is VD vector. Now try to resolve this into components. So to which direction we need to resolve, I mean why we need to resolve, so those things will come. So now we have evaluated the velocity of point D with respect to the member OA. Now D again is a point of the member CB. With respect to CB, it has two motions. It is not only rotating but also sliding in the slot in the member CB. So it will have two motions. One is a rotary motion, so which is like a motion perpendicular to as the same way we have seen earlier. So it is like perpendicular to the link, which is now it's a BC. BC is a link, or about the point D is that CD is the, so it should be normal to that particular location. So this is one of the component of the velocity. It's a rotary component, and a sliding component, which should be the sliding motion should be along the slot, right? So another component will be along the slot this way. So now if you see, as I mentioned earlier, now we can understand why we need to resolve this VD. So for the same point, it will have the velocity is now transmitted. So from the link OA, you can assume the point D is getting a velocity VD. Now when it is transmitted to the link CB for the same point, it has two components, the tangential component and the normal component. Normal component is causing it to slide along the slot. The tangential component is basically the rotary motion for the link CB. So now we just need to evaluate. So if we want to resolve, so VD is known, we just need to resolve this. So for that we need this angle, right? So that we can take the cosine of that angle times VD, magnitude, we will get the VD along the tangential direction, that is this component. So for that we need the angle. So why do we need that component? That's a so if you see, let's say this is VD component in the tangential direction. So the VD in the tangential direction, you can see it's just considering the member BC or the length CD in that member, just CD times the angular velocity of C, angular velocity of the member BC, right? So if the member CB has an angular velocity of omega CB, that times the distance CD should give the velocity of the point D in that particular direction, right? That's what we wanted. So that's why we need the component VDT. The basically magnitude only we need. Direction anyway we will it will be anti-clockwise. So it's a trivial. That's why I just said that. I think that's clear. So we need the that component VDT. So for that we need this angle. So let's say this outer angle V phi. We'll evaluate that. So if that angle is phi, and so this angle theta is already given. Theta is 45 degree. We need to evaluate phi. So let's assume this angle being phi, then evaluate this angle in terms of phi, this unknown angle. So if this angle is phi, then this entire angle should be phi, and this angle is theta, so that means this angle is theta. Now that means this angle, which is between the horizontal blue line and the normal velocity component, so that angle should be phi minus theta. So if that is phi minus theta, and so that angle we found it is phi minus theta. So now we need to know this angle. So this angle is unknown. Let me see. Yeah, so this angle should be, this angle, so that angle along with phi should make 90 degree, right? Because if you see that OD to along the line OD, so to the line OD, the vector VD is normal, so that total should be 90, so that this angle should be 90 minus phi. Now if you consider the resolution of the vector VD along the red color marked vectors, that is this 90 degree. Now that 90 degree constitute a phi minus theta and a 90 minus phi and an unknown question mark. So the total should be 90. So if you solve for this, we will get the unknown value to be exactly equal to theta. Let me verify that. Yeah, again I made a mistake, sorry. So this angle cannot be 5 minus theta. That I already denoted that is theta, right? But this angle is that is 5 minus theta. Okay, so in our expression, what change will come is that so again here theta, so just from the previous expression the idea is same. We are again considering the 90 degree which is created by the red color arrows, this 90 degree. Just earlier I had a wrong angle, so now this theta along with 90 minus 5 along with the unknown question mark is making the total 90 degree. So now if you solve, no, it's not 45. So 45 is theta, but theta is already given 45, but the unknown angle question mark, you can see it's actually 5 minus theta. So this angle I was talking about, which is 5 minus theta. Now still we haven't detected what is phi. That we will do now. Theta is already given. So if we know phi, we can say phi minus theta, which is the angle VD is making with the VDT. So the tangential direction. So now how to detect phi? So now if you consider the triangle COD, which is this triangle, excuse me. So this triangle, it's an obtuse triangle, so it has 3 angles and 3 sides. So now use a sine law, that is sine law for the triangle. So S by sine of the opposite angle to the S, which is 5 minus theta, equal to B by sine of the angle opposite to it, which is sine of theta, and the length CD by sine of the angle opposite to it, which is 180 minus 5. Sine of 180 minus 5 will be just sine phi, right? Now here just substitute the known quantities. So S is known, which is 0.1 by sine of phi is unknown, we have to evaluate. Theta is known, which is 45 degree, equal to B, which is 0.25 divided by sine of theta, which is 45, equal to length CD, which is unknown, divided by sine of phi. Again phi is unknown. Now if you use the first two of them equate and try to solve, we can evaluate sine of 5 minus 45 equal to 0.1 times sine of 45 by 0.25, which is, let me evaluate, which is 0.28. So now if I invert it and find 5 minus 45, which is which is 16.43. So from this we can evaluate what is phi, which is just 45 plus this value, which is 61.43 degree. So now we know what is phi, but what we really want is phi minus theta for the moment, because we have to evaluate, if you see the figure, the tangential component of the vector VD t. So VD t, the magnitude is whatever value of VD times cosine of phi minus theta. It's projection along that particular direction. So VD we already evaluated, which is 0.05 meter per second. So it's 0.05 times cosine of phi minus theta, that is phi minus 45, which we already have here, which is 16.43, right? So if we just evaluate it, we locked in, it is 0.04796 meter per second. So this is the component in the tangential direction of the link CB or BC. Now, as I mentioned earlier, we will use this formula. The tangential component of velocity at D with respect to the length CD is just the length CD times omega CB. So we need to know CD also, because both CD and omega CB both are unknown. But from this expression, the sine law, now if you use the second and third of the terms in the equation to be equality, then we can rearrange it to write CD equal to 0.25 into sine phi by sine 45. Now here phi is known, right, because we already evaluated phi. So it's 0.25 times sine of phi, which is 61.43 degree, divided by sine of 45 degree. So just evaluate it. We will find the length CD is 0.3105 meter. Now we can use this particular expression. Okay. From that, if we rearrange it, we can write omega CB is VD in the tangential direction divided by the length CD. So I hope that expression is clear. It's just the tangential velocity of the link CB at the point D is just the angular velocity of the link CB times the distance CD. We are just rearranging that to obtain the angular velocity. So we just substitute the value 0.04796 divided by 0.3105. So we'll obtain 0.154 radian per second. Yeah, so that is the answer. Any question? Is it clear? Good. So we'll move to the next problem. So here a rigid rod of length 2.5 meter slides down a smooth dome of radius 2 meter as shown in the figure. So assume the points A and B are very tiny point masses, neglect gravity. The velocity of A is given to be 0.5 meter per second. Direction is also specified. Then which of the following statements are true? So it's an MSQ, so there can be more than one answer being correct. If you see the options, you have to evaluate the angular velocity of the rod and the speed of the point B. velocity of B. So these two things you have to evaluate to identify which of the options being correct or wrong. Just try this out. If you are not able to do it, just inform me. I'll start immediately. Otherwise, I'll wait for some time. Better you try first and then I can explain. Are you able to solve this? Should I explain? Okay, so we can do it in different ways. So now I am going to use a geometrical method, though it is not completely geometrical. The idea is from the geometry. So basically the idea of instantaneous center. Now the point A is actually sliding along the horizontal surface. So it's not a curved path, it's a horizontal surface, or you can assume to be it's a curved surface of infinite radius, right? And and point B, which is actually along a curved surface. I think it's a spherical surface of radius 2 meter. So it will be always follow the curved path. Now the velocity vector at point A as given, it should be always parallel to the surface. But velocity vector at point B, it should be tangential to that point, right? It will not be along the length AB. It should be tangent to the circle, right? Because it's trying to move along the circle. Remember, there is no gravity, it's just that A is moving along, so you can think it is on a plane, horizontal plane. So this system is in a horizontal plane and just A is moving, so A is moving in the along the plane. So B is tied to or restricted to move along a circular path in that particular plane on the surface. So because of the motion of A along the horizontal direction along a straight line, B is also pulled along the curved path. So now we got the velocity vectors. Now you know what to do in the instantaneous center method, right? So let me read all the system again here. So the velocity vector at A is pointing in the horizontal direction, and at B it is pointing this direction. Now just need to extend the normal to the velocity vectors at both the points. They will meet at a certain point, which is the instantaneous center of the link AB, about which the link AB is rotating, a pure rotation motion about the point I. This is for the link B because for the link AB, because we are considering 2 points in the link AB, A and B. We know their direction of velocity. At point A, it should always along parallel to the horizontal line. So we just need to draw the normal to that velocity vector. It should meet it should reach the center of rotation, right? At some point, we don't know, right? Let it extend to infinity. Now B is also a point on the same link AB. So if you try to, so if, also the direction of the vector B, velocity vector at point B, because that is for point B, and the point B is actually trying to move along the curved path. So it should be tangent to that curve. Now if you try to extend that normal to that velocity vector, it's going to meet at certain point I. Now what are the things? So this is now geometrical thing. Now we know this should be 90 degree. These things are 90 degree. So the 90 degree is to the velocity vector VB. Okay, and this is V, not to the rod. Rod is this. The angle to the rod we have to evaluate. We will do that. And this angle is given 70 degree, and this angle is unknown. Let's keep that as alpha. So we have to find the angular velocity of the rod. So if you come here and see geometrically, the point A, we know the velocity VA. We can write the velocity in terms of the angular velocity of the member, AB. So basically, if you see, you can assume that member AB along with the I is making a triangular piece, right? It's an imaginary piece there. So you can think this as a single piece, just that that part is missing. This entire triangular piece, it's a rigid piece which is rotating about, pure rotation about the incident center, right? That's the definition actually. This piece is, it's like actually absent, that it's happening only at that instant. Next instant there will be another piece which is forming with a different incident center. But AB is a rigid material, always it is there. So at an instant you can think this is what happened. The ABI is a rigid material, assume, so that it is rotating about the point I with some particular angular velocity omega. So which is because just AB is the only real part, really existing part, I am denoting that as omega of AB. Or you could ideally think it's an angular velocity of omega ABI, about that particular center. So or you can just call it as omega itself. So to avoid confusion, I am just calling it as then omega. This omega times the distance to the point A, right, measured from the N center, so which is IA. So we need to know the length IA. If we know the, so that we can actually use geometrical arguments to evaluate what is the length IA. If we know that, then we just divide VA. So from this expression, it's omega times IA. So if we just divide this, we will get angular velocity, which is VA divided by IA. So now how we'll find IA? So we know the length of the road AB is 2.5, right? I think it's given in the question. And the radius, so let's denote this as origin. OB is 2 meter. Now what is OA? What is angle alpha? So now if you see here, let me draw a blue vertical here and denote this as C. From geometry you can see the height BC, which is equal to OB times sine of 70 degree, right, which is also equal to AB times sine of alpha. Now from this expression, OB is known, which is 2 times sine of 70 equal to AB, which is also known, 2.5 times sine of alpha. So only alpha is unknown. If you do it, we can find sine of alpha being 2 sine 70 by 2.5. Let me evaluate it. It is it's 0.752. So you can evaluate what is alpha. Which is 48.74 degree. So now we know what is alpha. Now so our objective is to evaluate the length IA, right, to use this particular equation. For that, we have a triangle OAI, which is a right angle triangle, whose one of the side is IA, and we know its opposite angle 70 degree. IA is an unknown. So if we know any one of the side, then we can evaluate the length IA. So that's what we are trying to do now. So right now we have evaluated the angle alpha. Now you can evaluate the one of the side, which is OA. How we will do that? OA is actually OC plus CE, right? Now OC is just 2 times cos 70 plus CA is 2.5 times cos of alpha. Now we know everything, 2 times cos 70, and alpha is also known. So let me substitute what is the value of alpha, which is 48.74. We just evaluate it. So we will get the length OA to be 2.333 meter. Okay. So now if we consider the triangle OAI, it's a right angle triangle, tan of 70 is IA by OA, right? So from this, IA can be evaluated as OA times tan of 70. So OA is, we just evaluated, 2.333 times tan of 70. So we will get this distance to be 6.41 meter IA. Now if we come back to equation 1, okay, we'll just do the omega is VA by IA. VA we already know, it's given in the problem. Velocity of A is 0.5 meter per second. So we just do 0.5 divided by IA is 6.41. So we'll get it the angular velocity to be 0.078 radian per second. So that's angular velocity. If you see the options, you can see option B has that angular velocity has a magnitude of 0.078. Now velocity of B, the point B, we need to evaluate. So again, the point B is in the same member as AB, which is forming like a rigid object, like an imaginary object ABI, right? So it's belonging to that particular object. So velocity of B, we can just write its angular velocity of that particular member times the distance to the point B from its instantaneous center, which is IB. So we need to know what is IB. Geometrically you can see IB is not exactly the diagonal, but if you see the triangle OAI, it has a diagonal of OI, out of which OB is known, which is 2 meter. If you subtract that, you will get IB. So that's what we are going to follow. First need to find what is the diagonal OI. So we can just, we know already OA, so we can just from the, we can just take OA square plus AA square root. So that will get OI, which is OA square plus IA square and a square root. So let me evaluate that. So OA is evaluated to be 2.333, right? And IA is evaluated to be 6.41, right? So OI will be 6.821 meter. Now OI contributed by OB and BI. So we only need BI or IB. So IB will be OI minus OB. So which is 6.821 minus 2, which is 4.821 meter. Now we use that here for velocity of B. We will find it's omega. Omega is already known, which is common for B also, because it's belonging to the same object, right? They will have the same angular velocity, only their velocity will be different. Angular velocity will be same. So this times 4.821. So the angular velocity is 0.532 meter per second. Okay, so I think I made a mistake somewhere. Let me check once. Yeah, small mistake in the evaluation. We'll do it again. Yeah, it's 0.376 meter per second. Okay. So that means option C is correct. Now if you again see, what we found is that velocity of B is 0.376 meter per second, and given velocity of A is 0.5 meter per second. So that means velocity of point B is lesser than velocity of point A. I mean the speed, magnitude of which. So that means option D is also correct. So all the three options are correct. So that's all. Any question in this problem? So I think that's clear. So because of time constraints, I am planning to stop now. So I have some more problems. I will upload these problems in the drive folder so you can access it. So this is another problem which is identical to the earlier problem. Unlike earlier we had a curved path, here we have a straight path. So it will be a little easier than that. But here one extra thing that you need to evaluate is angular acceleration. So this you can try in the earlier problem also. I stopped here, but you can continue to evaluate the angular acceleration. So only angular velocity of the rod we had evaluated, that we can evaluate the angular acceleration also. So the formula you have to use is that acceleration of point B is acceleration of A plus so it will so it's basically the relative acceleration we are considering. Now acceleration of B with respect to A. Now which will have two parts, a normal acceleration and a tangential acceleration. So the normal acceleration will be minus omega square times RBA, and a tangential acceleration which will be, let's say it's so where omega is angular velocity of the rod, omega BA, and let's say alpha BA is its angular acceleration, which for this planar system which will be k cap, generally it is a vector times the RBA vector. So this you have to incorporate while solving this problem. Other things are just same, just you have to first locate the incident center. So velocity of A is given, just divide that with the distance to the incident center, you will get the angular velocity of the rod AB. Same for every part of the body A to B to incident center. I am basically saying consider the imaginary triangular object which is connecting from AB to IC. In the entire triangular, it's like an entire triangular object is rotating about the IC. So wherever I take a point inside the triangle, all will have the same angular velocity, which is common for all of them. So you first evaluate the angular velocity with respect to A, and which is same for B also. Just that the distance of the point B from the incident center is changing. So if you multiply with that distance, which is I to IC to B, which is actually 4 meter here, to the angular velocity which we have evaluated earlier, you will get the velocity of B. Now the direction of velocity, it's actually obvious. B is trying to move along the horizontal to the plane, so it should be horizontal direction. So now come to acceleration, you have to consider this equation, which is basically the relative equation for the relative acceleration with V and U. So just try to solve this. I will upload this with the solution and 2 or 3 extra problems, and try to solve yourself. So any other questions?
No, sir.
Okay, so then we will stop here for today. So we'll meet next week. Thank you.